Hi everyone. Today we'll try to understand what are deep deterministic policy gradient (DDPG) algorithm and reinforcement learning. So in my previous videos, I've already covered basics of reinforcement learning, MEB, contextual MEB, algorithms based on deep reinforcement learning like A2C, reinforced algorithm, DQ, and etc. This time we'll be moving ahead with deep deterministic policy gradient, aka DDPG. Now, what is the difference in DDPG and other algorithms? So in the previous algorithms that we have already discussed in my previous videos and blogs, the action space is usually discrete, while that state space is continuous. What does this mean? This means that the action that the models are trained were discrete in nature, like left, right, up, down, accelerate, deaccelerate, but not like apply point 0.5 brake or move 32.3 degree to the right or steer 35 degree and accelerate by 10 kilometers per hour. This means that we are not doing any quantification. We are taking the action, but no quantification was associated with that. Ki how much acceleration should I do? How much should I move to the right? Right. So when we have a continuous action space, in this case, DDPGs can be of a great help. DDPG also belongs to the family of actor-critic methods. So one of the previous algorithms that we discussed, advantage actor to critique, was also from the actor-critic method. So to know what are actor-critic methods, you can refer to my last video. Uh, but A2C was more towards discrete actions. DDPG is more towards continuous actions. So we will try to understand how DDPG is different from A2C, and then eventually we'll try to train an OpenAI gym environment with codes. We'll try to understand the codes as well. So I'm assuming that you need to have an understanding of advantage actor to critique method, or basically actor to critique method, to understand DDPGs, which I've already discussed in a previous video. So a few things that we have that has been changed in DDPG compared to A2C is we would be now using target networks for both actor and critic for stabilized training. Second is a use of an experience replay that we eventually use in DQNs, and the loss function for both actor and critic has been updated. So we will be discussing about all these 3 points in some detail now. So what is experience replay? That already I've already covered in my previous video when I was explaining about DQNs. So you can check that out. So actor to critic method, advantage actor to critic method doesn't use an experience replay, but in case of DDPGs, they would be using an experience replay. Second is the loss function. So this is quite critical. So the loss function has been updated. So in case of critiques loss, the critiques loss is mean squared error between target Q value and estimated Q value, where the target Q value is reward plus gamma into target Q network, target critique network future state, and target actor network future state. So I will be telling you what are target networks also. So target networks are nothing but a copy of the actual actor and critic network. That's it. So why we are using target networks? Basically because target networks helps in stabilized training. So what happens is that whenever we are training the actual models batch by batch, we won't be updating the target networks that frequently. So only the frequency of updation changes in case of an actual network and the target network. So in the critics loss, as you can see that the critics loss is nothing but mean square between target Q value and estimated Q value. Now, the point to be noted is the target Q value formula, which is reward, quite easy, plus gamma into target critique network, which intakes future next state, and target actor predicting actions for the next state, right? Whereas the actor's loss is now minus critic minus q value for the current state action pair. So q means that it is the actual critique network. Here you can see a is actor network, as mentioned here. Q is the critique network. T is target actor network. TQ is target critique network. S is current state, as is mentioned here. In actor's loss, it is not mentioned critiques loss right now. Estimated q value it would be used, and s bar is next state. So now the next question is, what are target networks? So target networks are nothing but a copy of the actual actor and critique networks, which are updated with the actual network counterparts periodically. So for example, assume that for actor network we have a target actor, and for critic we have a target critic. So there would be four networks that we would be training. Just remember this, and assume that we are updating the weights for the actor network after every after every epoch. So it can be the case that for target actor network we would be updating the weights after every 5 epochs or 10 epochs. Just the update weight frequency changes between the two, else everything remains the same. So it is believed that by using an target network, the training becomes more stabilized, the convergence is faster. That is what target networks are used. So now we have understood our loss function, and we have also understood what are target networks. So let's try to understand the environment for which we would be training today. So we would be training over pendulum V1 from OpenAI Gym. So let's understand the environment. So in this case, the action value can lie between -2 to 2, which is actually the torque applied. It is basically some physics coming in. So I won't be jumping deep diving into the mechanics of the environment. But -2 comma 2 is the range in which the torque applied can be estimated, and the state space consists of three values. One is cosine and sine angles, and angular velocity of the bar. Now the reward function is the continuous value designed to encourage the pendulum to be upright and balanced in the upright position. So basically, in this video, in this particular GIF, you can see that it is downwards. It has to be upwards so that the reward would be higher in it. Reward would be less negative in nature. So if you look into the reward function, it is minus theta square plus zero point 0.1 into theta underscore dot square plus 0.001 into action square. And here you can understand what is theta underscore dot, and action. A goal of the whole environment is to keep the bar, the pendulum that we have, it has to be upright and it has to be as straight as possible. So now we will move on to the codes. So basically, first code snippet is nothing but inputting all the important libraries. Second is initializing the pendulum V1 environment and considering the num actions and input shape. So num actions equals to 1 because we will be taking just one continuous value between -2 to 2. Right. Declaring actor and target actor network. So here you will understand the whole concept of how target network is different from actor. So the architecture remains the same. Here you can see that we're using the same function to initialize both actor and target actor. It would be just during the updates that the two networks will differ. So actor network is nothing but a feed forward network, as you can see that. The only point to note is the activation function that we have used, that is 10h. We are using a 10h function because if you have noticed, the action value is -2 to 2. So the output from a 10h 10h activation would be scaled between -1 to 1, and eventually we'll be scaling it to -2 comma 2. We can't use a ReLU here because it would have given a value from 0 to infinite, right? And we want to have negative values in the final output. That is why we are using a 10h. Similarly, if you look into the critique network, here also we have declared the critique network alongside the target critique network. It is quite same. So in case of an actor network, it was in taking the current state and eventually outputting you the action. In case of a critique network, it is in taking the state alongside the action and then predicting your Q value. So it is also quite easy. It is also majorly a feed forward network, but but somewhere in the middle here you can see the concatenation happening. So we are having two inputs, state as well as the action. So there would be a point where we would be concatenating these two to form a single embedding, and then eventually moving ahead where we have the last layer as a dense one with activation equals to linear activation because Q values can be any continuous value, and the output would be just single value because for any state and action pair we'll be having a single Q value. I think the actor and critique networks are quite clear. Now, this is a particular function that we would be using to update the target networks, right? So here you saw that we have declared the target networks as as similar to their actual counterpart. So here also the same function has been called for actor also, actor comma target actor getting initialized with the same function. Similarly for critique and target critique, they are getting initialized with the same function. For updating, we would be using a hyperparameter called as tau. So in this particular line here, you can see that the target actor weights would be updated using this particular equation: tau into actor weights plus 1 minus tau into the target actor weights. So it's very easy. So basically it would be an amalgamation of the two weights where using tau we are maintaining a trade-off between the two weights. So it's not that we are simply copy pasting actor weights to target actor weights after some epoch x. It is not like that. After some epoch x, we would be considering some portion from actor weights and and remaining portion from target actor weights. Hence, tau is a very important hyperparameter that has to be tuned up. In this particular code, it hasn't been tuned up, and I have gone with the very default value of 0.05. But you might need to tune it up for implementation purposes. Similarly, for critique weights, also here you can see that the target critique network is also getting updated in the same way. tau into critique weights plus 1 minus tau into target critique weights. Now we have also introduced a noise function. So basically, it was mentioned that by adding some noise, we can by adding some noise to the action predicted, we can save the model from overfitting. So this is the noise function that I've simply copy pasted. So I don't think so. We even need to understand key what is the logic behind the noise function, how the noise is getting generated. Here you can see that how in the noise that we are generating, we're adding a noise term. Just this is the important part, that the noise term has been generated using exploration noise object that we have passed here. That's it. I think we don't need to jump into the detailed information of how the noise is getting generated. This line is crucial, that we are how we are adding noise to the action and eventually clipping the action value between -2 to 2. Now there are few constants that we have declared that we would be using for the training purposes. The basically the important one is the replay memory, experience replay memory. So I am assuming that you have seen the video on experience replay on my channel. So eventually you would have understood the concept of experience replay. So the length of the experience replay is 1000. Now we'll be moving on to the training loop. So basically, for every episode, we are resetting the environment, and then eventually, if you see, we are using the state, we are feeding the state to the actor and predicting the action for it. So if you remember that we are using a 10h activation in the end, so we are rescaling the 10h activation by multiplying it by 2. So if the value output is -1, multiplying it by 2, it becomes -2, right? Once we got the action, we are adding some noise using the DDPG add exploration noise function that we declared above, and then feeding this action to the environment to get next state, reward, and done status. Done status is basically whether the episode has ended or not. And then we are appending the current state, the action, the reward, the next state that we have got, and the done status into the replay memory. I think this is very similar to what we did in DQNs also. Now, once we have got a threshold number of samples for training purpose in the experience replay, what we are doing is that we are again getting each and every element from the experience replay and converting it into tensor. We can ignore this part. Coming to this one, q underscore actions equals to target action. So using the target action, a target actor network, now we are trying to calculate the target q value in this particular line, target underscore q value. So as I told you that for calculating the target q value, if you remembered, we were using just the target networks, both target actor as well and target critique value. So first of all, you will be calculating the actions that has to be taken on the next state using the target actor, and eventually using this q action as an input for the critique, a target critique network. Here you can see that the q actions that are getting predicted using the target action, target actor network, we are feeding that alongside the next state to the target critique network now to calculate the target q value. And by applying gradient tape, we are calculating the current q value using the critique network. Just remember that the target q value would be using the target networks, and the current q value would be using the actual critique network, and then calculating critiques loss using reduce mean over target q minus current q value, and then applying the gradients to the critique network. Do remember that we are not applying the gradients to the target critique network right now. Similarly, for the actor network, here you can see that we are using the actual network, using the taking the current state as an input to produce the actions, and then using actual critique network, we are producing the current q value, and then we are doing a minus of negative mean of current q values that has been predicted by the critique network to calculate actors loss, and then applying the gradients over it. Now here you can see that after every fifth epoch, or you can call it fifth batch, I think it's a terminology mistake, I'm calling it update target network. So if you have noticed, after every batch, the actor and critic would be updated, but target actor and target critics are not getting updated. So they would be updated when we get to this particular criteria. That is, if epoch mod 5 equal to 0, that is the frequency of updates for target critic and target net actor is lesser as compared to the actual actor and actual critic. Yeah. Now, this is the code snippet that you can use to visualize the output using the trained actor network. This has already been explained in my previous video using Pygame. So you can refer to that to understand the code snippet that we have here. Now talking about the end node after the training part. So eventually I use this code snippet to train my pendulum V1, but the results are poor. So on exploring over the internet, I figured out that DDPGs are very hard to train because of two major reasons. One is that they are very susceptible to hyperparameters. So if you have seen that we were using a number of hyperparameters, be it gamma, be it tau. So tuning hyperparameter is very important. Second thing is that as you have noticed, GDPG is acting on continuous action space, right? So our earlier games that we were training were based on discrete action space, so they were easier to train. Here the exploration part is very huge, so it requires a humongous amount of training to actually lead to reasonable results. So I'm assuming that do try this code out. You can try to train other agents present, other environments present in OpenAGM like car racing and all, and try to tune these hyperparameters also for better results.